Hello, and welcome to a lecture about earthquakes. As we've previously discussed, earthquakes result when sudden slip happens along a fault plane. Faults form when tectonic forces add stress. So, first you got to make a fault, and then, thanks to tectonic forces, you've got to cause slip to occur on that fault plane. When slip occurs on the fault plane, energy that is stored in the rocks, thanks to the tectonic stresses that are being applied to those rocks, gets released and takes the form of seismic energy. Seismic energy is usually released into the earth in the form of waves, which we'll talk about in just a moment. Faults move in jumps. So once movement starts, it quickly stops due to friction. Over time, strain builds up, leading to repeat failure. This is called stick-slip behavior. So sometimes we like to use an analog for this that's called a dashpot, where you have a block that is sitting on a piece of wood and a spring attached to that block. So imagine that you pull on the spring. You are actually putting energy by pulling backwards with your hand on the spring, but notice that the block is not moving. And it's only when you overcome the frictional forces that are holding the block to the wooden surface that the block all of a sudden slides. That is analogous to slip all of a sudden occurring on a fault surface after many, many years or thousands or millions of years of tectonic forces being applied to the rocks on either side of the fault. After slip occurs, stresses drop way back down and are now low again because the block's caught back up to your hand. And so now, in order to build stress back up, you've got to pull on that spring again until suddenly slip will occur again. This is what we call stick-slip behavior, and this is how most faults in the earth behave. Very often, major earthquakes are preceded by foreshocks, but that doesn't necessarily have to be the case. You've probably noticed in the news when we've had earthquakes in our area that when an earthquake occurs, the professionals that they interview about the earthquake will say that if this is a foreshock, then we should expect another larger event in the next 24 hours or so. And very often that doesn't happen. So we know that the event that occurred was the real event and not just a foreshock. But sometimes earthquakes can be preceded by foreshocks, which may forewarn of an impending large earthquake. Similarly, earthquakes can be followed by aftershocks. Large earthquakes almost always have these, and they can occur for weeks or even years. Aftershocks can be somewhat large, but are not usually as large as the main event. So in this picture, we're looking at a map of earthquakes that occurred, strangely enough, in Virginia. So you can see the main event is the bright red circle. The circles are scaled by earthquake magnitude. So the red one was the initial or primary earthquake event, and it is the largest. And then as time went on, the color of the circles becomes more and more cool. So going from orange to yellow to green. That is what's shown over here in this scale bar. So this is the main event, and then after an hour there are a few of these orange events, and then after a day a few of these yellow events, and then even a week later getting some of these green events. And you'll notice as you go from red to the orange, yellow, green, the size of the circles is getting smaller. So the magnitude of the aftershocks is also getting smaller. Earthquake energy travels through the earth in the form of seismic waves. Okay, there's a number of different ways that we can categorize seismic waves. This is just one way that we can think of breaking them down into different parts. We can think about waves as being those that pass through the interior of the earth. We call those body waves. And waves that travel along the surface of the earth, and we call those surface waves. For now, let's just focus on the body waves. Body waves can be further divided into two main types. The first we'll call compressional or P waves. Sometimes you'll see P waves as standing for primary waves. I'll explain in a moment why these are called compressional. There's another type of wave called shear waves or S waves. And sometimes you may see the S referred to as secondary, although really we like to think of the S waves as being shear. Either way though. P and S is what I want you to remember. P waves and S waves. These are both body waves. They travel through the interior of the Earth. Surface waves, for the most part, we're just going to lump into one category, just call them surface waves, but they can be further broken down if we want to into those that act like a snake. Think about like a sidewinder moving across the Earth. We call those love waves, or Rayleigh waves, which act like a roller coaster where the ground is going up and down. And it is surface waves that you feel during the shaking of an earthquake event. And you've probably even experienced both love waves and Rayleigh waves when you feel the earth kind of vibrating, and maybe you've even felt that kind of rocking and rolling sensation. That's usually because you're feeling both of these surface waves. Okay, P waves, primary or compressional. That's kind of what the P stands for. Think about P waves as being like a slinky, wherein the propagation direction of the wave is also in the vibration direction. So if you pull back and forth on a slinky, you'll notice that the slinky will expand and contract. That's the vibration direction, and that expansion and contracted part will actually migrate or propagate through the slinky in the same direction as the vibration, like so. This is something that is very difficult to illustrate in a flat image like this. So please come to our next class meeting where we're going to look at a video of this together. S waves, secondary or shear waves, are also body waves, and they travel by moving material back and forth perpendicular to the wave travel direction. So in the last picture, the vibration direction was parallel and in the same orientation as wave propagation. And in this case, in the case of S waves, the vibration direction is perpendicular to the wave propagation direction. Because of that, S waves tend to move slower than P waves, and they only travel through solids. S waves never go through liquids or gases. Incidentally, that is how we found out that the outer core of the Earth is liquid, because S waves that were generated by earthquakes on one side of the planet were not recorded at seismometer stations on the other side of the planet, because of course those earthquake waves would have to pass through the center of the Earth to get there because they're body waves, and the S waves never made it through the center of the Earth, through the outer core. That's how we knew that the outer core had to be solid, because the S waves didn't get there. P waves, however, can travel through any material, and they move the fastest. So when an earthquake occurs, the P waves will travel the fastest through the Earth and will be always, always, always the first earthquake wave to arrive at any recording station. Surface waves, I've told you, can come in two forms. They can be like the sidewinder snake. Those are the L waves that we're seeing here. They can also be like the R waves or Rayleigh waves, and this would be like the roller coaster version of surface waves. Surface waves, they travel along Earth's exterior, along the surface, of course, and I've already told you these are the ones that you feel during an earthquake event when you experience that shaking. They are the slowest, so they are the body waves, the P and then the S waves, are the first waves to propagate away from the earthquake hypocenter or focus. The P wave moving very quickly, the S wave moving quickly, but not quite as fast as the P wave. And it's only when these body waves reach the surface that they generate the surface waves, which are the slowest and always the last to arrive. Because they are physically moving the surface of the Earth back and forth and up and down, they are the most destructive and cause the most damage to buildings and infrastructure at the surface. So how do we know when an earthquake has occurred? They get recorded at seismograph stations, which are built into the bedrock of the ground and are located all over the Earth. So we can't have seismograph stations in the ocean for obvious reasons, but on the continental crustal land masses, there are lots and lots and lots of seismograph recording stations. So how do seismographs work? They are simply instruments that record ground motion. And they work by having a weighted pin that hangs. The weighted pin hangs. And a rotating drum is oriented, can be oriented either vertically or horizontally, like what is shown here. And sometimes we do both in order to capture both the vertical and horizontal motions. When the weighted pin hangs on a spring, that's what's shown here, so it stays stationary. If the earth moves up and down or side to side, that weighted pin on the spring never changes its position, because the spring contracts and expands to accommodate the weighting of the pin. So no matter what, the pin doesn't move. The rotating drum, however, which is attached to the seismometer, does move up and down or back and forth. And so relative to the pin, it will create these crazy waveforms that you're seeing here. And those waveforms become the seismogram. Seismographs, these instruments, are bolted to bedrock and are usually sheltered because we don't want to be picking up random vibrational energy that might occur because of, say, trucks or whatever in the landscape. And again, in this picture, this would be our weighted pin. So here's the spring, and here's our weighted pin, and it's just hanging out there. It's kind of buzzing along the rotating drum of paper. Nothing is happening, so it's mostly a straight line. But when an earthquake occurs, the ground surface will go up and down and or side to side, and the weighted pin won't move, but you can see that the drum is actually moving up and down. So this line is the reference line, and notice that the weighted pin in all cases during the earthquake event stays at the same reference line. But as the ground goes up and down during the earthquake event, so does the rest of the seismograph, including this drum. And so therefore, up and down motions get recorded on the seismograph. And they take on these I don't know what to call it, jaggedy wave-like forms. Here is the resulting seismogram that might get recorded at a seismograph station immediately after an earthquake event. So over here, we've got the weighted pin just hanging out, recording that reference line. The ground isn't moving, nothing's happening. When the P wave arrives, it makes a very slight zzz vibration to the ground, and so we pick up the P wave arrival. P waves will always arrive first because they're the fastest. So there's our P wave arrival. S waves arrive next, the second type of body wave, and produces a larger amplitude of motion at the seismograph. And it's not until later that the surface waves, which are these here, start to arrive. And look at the amplitude that gets created during the surface waves. That shouldn't surprise you, given that the surface waves are really going to move the ground to which the seismograph is attached vigorously up and down and side to side. So a few things to note here. P waves always arrive first, followed by S waves, followed by surface waves. P waves will be the smallest in terms of the amplitude that gets recorded on the seismogram because they're just like a really, really fast vibration, a compressional vibration that moves through the earth. They're not going to create a lot of up and down, side to side motion in the earth. So therefore you won't have huge amplitudes in the seismogram. S waves will be slightly bigger, and then the surface waves are going to create really large amplitude shaking events that get recorded on the seismograms. Let me back up. That's what we mean by these arrivals that get recorded here. Here's the S wave arrival. So this is time 1, P wave, time 2, S wave, time 3, surface wave. The seismograph tells you when seismic waves arrive at a given location. So that's when we say that the seismic waves arrive at the given location, that's what the seismograph station records. They also tell you how energetic they are. The energy of the earthquake is proportional to the amplitude of the wave form that gets recorded in the seismograph. So something that goes like this is a much smaller earthquake event than if it does this. Okay, so that is the amplitude is a function of the energy. Importantly, however, the arrival times of the P and S wave can tell you something about the distance to the epicenter. If the P and the S wave arrive close together, as you're seeing in station 1, the P wave arrives here, and then the S wave arrives. And the difference in time between the P and the S wave, is about 5 minutes. At station number 2, which is here, and farther from the epicenter, notice that it takes longer for the P wave to arrive, so it comes in a little bit later. And then the difference in time between the P and the S wave arrival, that's a longer distance of time, maybe 7 minutes. Station number 3, which is even farther away from the epicenter, will record the P wave arrival later. And then notice this, the difference in time between the P and the S wave arrival, still longer, probably on the order of 10 minutes. The difference between the P wave arrival time and the S wave arrival time, which we call the S minus P time, is a function of distance from the earthquake epicenter. The larger the S minus P time, the farther away from the epicenter the seismograph station is. We can determine exactly how by using something called a time travel graph. And this is what you're going to be using in your problem set. The time travel graph shows the time it takes for both the P wave and the S wave to get to a seismograph station that's at a variable distance from the earthquake epicenter. So the x-axis is showing us distance between the epicenter and the seismograph station. So a seismograph station that's relatively close, 2,000 kilometers, that's still far, but that's at 2,000 kilometers, will have a P wave arrival time of 4 minutes and 6 seconds. The S wave arrival time will occur at 7 minutes, 25 seconds. The difference between those is approximately 3 minutes and 19 seconds. If, however, the seismograph station is farther away, like let's say 6,000 kilometers away, the P wave arrival will not get to that station until 9 minutes and 21 seconds have elapsed since the earthquake event. The S wave will not arrive until 16 minutes and 56 seconds. So something like, how many would that be? Oh, I don't know, over 5 minutes of SP time. This would be greater than 5 minutes. Whereas remember, this one down here was about, I said 3 minutes and 19 seconds. So we'll call it 3 minutes. So that looks like a 7, but this is supposed to be greater than. So the point here is that if the station is farther away, the S minus P time is greater. And we can actually determine the actual numerical distance from the earthquake epicenter by using these charts. So we know, for example, that if the P minus S time is exactly 4 minutes, then we would go and we would look for an interval between the S and P curves that is exactly 4 minutes difference. And then we would read it off the bottom of the chart here and say, oh, okay, that earthquake is 5,000 kilometers away. If you do this for at least 3 seismograph stations, you can then triangulate the location of the earthquake by drawing the distance radius on a map. When you draw 3 different radii on the map, 3 circles must intersect at a single point, and that single point becomes the epicenter. Tune in to discuss more of earthquakes with me on Thursday. Bye-bye.